This is Mrs. Palmer Quay with the second video for Module 7. In this video, I want to talk to you about electrons and how they are involved in the atomic emission spectra that we see for elements. Just a little reminder, we've already talked about how light is a form of energy. And when we use the word light, we are really talking about electromagnetic radiation, which comes in many different wavelengths and frequencies, some of which are visible light and other are invisible waves, such as radio waves or X-ray waves. All light, no matter what wavelength or frequency it has the same speed, though, in a vacuum. We also talked about how hot objects will give off light. And if electricity is passed through a gas, light is seen. That's how we get all of our fluorescent lights. And finally, something else that's part of this discussion is this discovery that light can cause electrons to be ejected from a metal. And that's known as the photoelectric effect. And it has a direct application to your calculators that are solar powered or just solar power in general. The photoelectric effect came about with the observation that when light hits a particular metal, in this case we have sodium given as an example, electrons are pushed out of the metal and actually off the surface. If you put that metal plate inside a vacuum tube, and so you have this plate on one side, and then you have another plate on the other side where the electrons can move to, we have moving charges, and moving charges produce electricity, and that electric current can actually go to be stored in a battery to charge a battery. And again, as I said, the photoelectric effect is what we use to create solar power, because the sun, the photovoltaic cells, the solar panels store the electricity in batteries, and then whatever system you have using those batteries then are able to use that electricity. But with the photoelectric effect, with the scientists that were first investigating this, they found a mysterious thing. They found that certain wavelengths of light did not do anything. For example, if blue wavelengths of light, as you see here, caused electrons to be ejected from the metal plate, well, red wavelengths of light, no matter how bright, how intense those lights were, or that wavelength of that light was, there would be no electrons leaving the plate. There was something about that wavelength, that red light, that didn't work, no matter how strong that light was. And conversely, this blue light, if it sent electrons off the metal plate, it would continue to send electrons off, even if it was very low intensity, very dim. So something about the color of the light really determined whether electrons would move. The color of light is determined by the wavelength, and along with wavelength always comes frequency. Waves with a low frequency have a long wavelength. Waves with a high frequency have a short wavelength. So there was some type of minimum frequency, a particular frequency, that was required in order to see electrons moving in the photoelectric effect. You should remember from the previous video that scientists have determined that light can behave not only like a wave, but also like a particle. And it's the particle theory of light which explains the reason for this minimum frequency required to see the photoelectric effect for any particular metal. This can be explained by thinking about the relationship between energy and frequency. Remember that energy is directly connected to frequency. I'd first written this equation as a physicist do with V for velocity, but your book will say that energy is equal to Planck's constant, this h, times the frequency of the light. And because there's a direct relationship between frequency and energy, we can say that energy can represent, or the E here is representing the minimum amount of energy needed to eject an electron at a particular frequency. So that if your right side of the equation, Planck's constant times the frequency here, is less than the energy required, no electron will be emitted from that metal plate. But if that combination of the Planck's constant number times the frequency ends up being a larger or equal to the amount of energy, that is the minimum amount required, electrons will be emitted. Frequency does not affect intensity. Intensity is a reflection of the amplitude. Something with low intensity has a low amplitude, and high intensity has a high amplitude. So the intensity of light has no effect, but something about the frequency, and then particularly the energy that that frequency represents, is what matters. So that light frequencies are understood to represent packages of energy, and we call those packages photons. And the different wavelengths of light then have different size photons. The photon for a red wavelength of light is different than the photon for a blue wavelength of light. The photon for red would have less energy in it because red light has less energy than blue light. Along with light going into atoms and making electrons come out, light can also come out of atoms. Under certain circumstances, electrons can absorb energy and give off light as a result. For example, our various noble gases over here, if electricity is passed through a vacuum tube containing that gas, they will give off light of various colors. Here's neon, the orange color that's characteristic of neon. Also, if you burn elements, here we're taking, there's a little, you can see a little stick here, a little compound or element is placed on the end of that stick. It's put in a flame, and different elements will burn with characteristic color. Lithium comes out pink, sodium yellow, potassium sort of purpley blue, copper nice and green. So energy, heat energy is being added to these elements, and colored light is coming out. How can we explain it? How can we understand what's happening to cause light to come out of an atom instead of light going in? A particular device called a spectrometer uses a diffraction grating to separate light into different wavelengths. Diffraction grating works like a prism, but it's made up of something that has many, many tiny slits in it. So the illustration here, white light is coming in to the diffraction grating, and when it comes out, it's separated out into all of the colors of visible light. Interestingly, if you put electricity through a gas or you heat up and burn an element, you see, and then look at that colored flame through a spectrometer, you see a unique collection of colors, a unique emission spectra. Light is emitted, and certain lights are emitted, and other colors are not. Here are some examples of emission spectra, what you would see if you looked through a spectrometer towards a burning element or a being heated element in a flame, or a gas that has electricity passed through it. On the top we see the visible spectrum. This would be what you would see if you looked at sunlight. You can see that we have all the colors of the rainbow, and they blend one right into the other. There are no distinct lines. But all the other elements have bright line spectra. Hydrogen only has 4 colors shown. You can see we've got 1, 2, 3, and 4 colors, but that's all. There's nothing here in this green and yellow and orange section. Neon has a lot more bars than hydrogen, and there's a big cluster here around the orange and yellows and reds, which is why it looks orange to us. Iron is even more complicated. It has colors representing the whole full spectrum, but they are not continuous. There are some blank spots in between. The dark patches are representing wavelengths that are not represented by this atom. When it is heated or electricity passes through a neon gas, a tube of neon gas, wavelengths of light are given off. We see light of a particular color, but there are wavelengths that are not given. And the question came up with scientists who were trying to figure out why are some wavelengths given off and others are not, and why every single time we energize neon it always looks like this. What is it about the structure of the atom that causes this to happen? The scientist Niels Bohr proposed a model for what was happening inside a hydrogen atom when light was given off, when it was energy was being added by putting the hydrogen gas in a tube and running electricity through it. And we use his explanation as a way to understand what is happening with all other elements when they are excited, are energized, and light is given off. Bohr's model says that when light comes in, if it comes in of the proper energy, and this equation here on this diagram has the speed and wavelength in the equation. So this c divided by the lambda, that's speed of light divided by wavelength, that's equal to frequency. So really this equation is the one that we are already familiar with, which is the constant times frequency. So if there's energy coming in, it's going to hit that electron, and this is a model of the electron where we have the nucleus in the center, and then we have electrons orbiting around the nucleus. So this electron is down here in this lower orbital. It's in the ground state. It's at the lowest possible energy, hanging out close to the nucleus. Energy comes in and is absorbed by that electron, and that electron cannot stay at that energy level of that orbital. They need to move out, and so it jumps out to this higher level orbit because it has extra energy. It needs more space to run around. But the electron doesn't want to stay out at that level. That is, it is energized, but it's not going to stay there. That's not sort of the normal resting condition. And so, and we call that excitation. This electron is excited over here. It's got some extra energy in it. But it is going to drop back to its normal place close to the nucleus. And in order to do that, it has to get rid of some energy. So it throws off that energy, and it throws it off as a photon of light. However much energy comes in, that amount that comes in is the amount that goes out. So there's an exact amount needed, and it is the amount that is represented by how much energy it takes to jump from this first level of the electrons, the first energy level, up to the second energy level. There's a certain amount of energy needed to have that happen. If this electron was going to move out to this second or to this third energy level, then there would be even more energy required. You would need a larger amount of energy, a bigger photon, something of a higher frequency. You have to have a larger amount of energy coming in order to make that electron make that bigger jump. And when the electron returned from that, if it was out here in the third energy level, if it returned all the way back down to the first energy level, then it would be given off that big portion of energy as light again to go out. So the amount in is exactly the right amount to make the electron move one energy level in its orbits around the nucleus, and the light given off is exactly how much it has absorbed, again representing how much energy it takes to move between levels. So this is the model we use to understand why different elements give out particular emission spectra. That the idea is that electrons only exist at discrete energy levels. There are only certain energy levels that they can stay at around a nucleus. When it's in its lowest energy state, we call that the ground state. But if we put energy in, either by adding electricity or adding heat, we can excite electrons and get them to move to a higher level. They jump from one to the other. And then they jump back and release that amount of energy as electromagnetic radiation when it returns to the ground state. So as an illustration down here, we see energy coming in. It's being absorbed by the electron, and so it jumps all the way from this level to this level. It's never found in between. This is a gap space that you only find electrons at this one energy level 1 or energy level 2. There's very specific amounts of energy that are required. And then when the electron drops back, a photon of light is released. And that explains the light that we see when we energize atoms and elements, either by heat or by electricity. The atomic emission spectra for each element is unique because each element has a unique number of electrons that can be energized and jumping around from different energy levels within that element and producing the light that's characteristic of those particular jumps. When all of those energy level jumps are added together, we get whatever color or colors that make up the atomic spectra, emission spectra, for that element. This technique has allowed us to identify what elements are present in stars, along with some forensic analysis of drugs and other interesting things that we are able to get at the elements by their fingerprints in atomic emission spectra. So this finishes up what I want to say for this module. We'll talk a little bit more about electrons and atomic structure on the next one.